So alright, the next subject is a design issue. Let's talk about the concept of allowable stress. So allowable stress in 우리말, it is called allowable stress is 허용 응력. 허용 응력. Excuse me. Okay, so now let's consider design issue. So here let's consider an easy example, simple and easy example. So I want to consider a bar. So we are discussing this example many times. So probably you are very familiar with this. So subjected to a pair of forces. Okay. And then because of this force, so we must have development of normal stress here. Okay. And then okay, let's imagine a realistic situation. Are you able to control a force like if you want to apply the force is 100 tons? So are you able to control the force is exactly equal to 100 tons? Actually, in reality, it is very difficult, isn't it? So that's why if you consider the magnitude of normal stress caused by the force, so let's consider the force, then we may have certain distribution, isn't it? Certain probabilistic distribution. Okay, this is distribution of forces. So what we sorry about it, the normal stress. And then this is what we control is we control only the average value of the normal stress. And that because of the stochastic nature of the forces or any external actions, we must have certain distribution. Sometimes the normal stress caused by the external force may be a little bit greater than what we intended, or can be a little bit less than what we intended, isn't it? This is the nature of probabilistic nature. Okay, probability. And then if we want to design the structure against this external action, so we have to choose a certain material which would provide better or the greater performance than the normal stress caused by the external forces, isn't it? So anyway, to guarantee the safety, the strength of this material, let's say strength of this material, let's say I want to call this as F, or I want to call the resistance, maybe that's better, the resistance of this material. And then if you divide the resistance of this material by the cross-sectional area, then we may have the resistance stress, isn't it? So if you test the material would have certain resistance. And again, so if you test the same material, there exists also probabilistic nature. So we have the normal stress, the resistance of normal stress, and then also there exists some kind of distribution, isn't it? Yeah. So if the resistance is greater than the normal stress caused by the external force, then it fails, isn't it right? It's failure. Then if it's safe. Sorry about it. It's safe. In the opposite case, the resistance of the material is less than the stress caused by the external force, then so we can imagine that this is failure, isn't it? Okay, so to guarantee this safe condition, so what we want to do is, so we want to make, this situation intentionally. The resistance is greater than, so I want to control always resistance is greater than any normal stress caused by the external forces or actions. Okay, so let's look at the lecture slide here. So if you look at the lecture slide, then I have certain material behavior, stress and strain here. And then as we discussed last time, there exists yield stress, and then probably there must be ultimate stress. But I don't want to, the stress caused by external force exceed the yield strength value. I don't want that. That's why intentionally, instead of using the yield stress value as the criterion, I don't want to compare the normal stress caused by the external force with the yield stress value, but instead of that, I want to consider a certain point which is less than the yield strength value. Okay, and this is the this is called the required strength. Okay, the required strength. So I want to compare everything to this orange point. Here we can we can have a concept of safety factor. So this is the actual strength. So here you may consider the yield stress value, and then for the design purpose, my normal stress is around this orange dot, so always less than the yield stress value. This is the strength that we use. Okay, the strength that we use. Then here we can obtain the concept of safety factor. Here the safety factor means in 우리말 안전율. Okay, 안전율. The safety margin is defined as n-1. Okay, n-1. Here, to avoid any failure here, if you want to consider yield stress as the reference value, where we determine failure or not, then I want to control, the stress caused by the external force is always less than this yield strength value, isn't it? So which means the required strength is smaller than the actual strength yield stress value. That's why the safety factor should be always greater than 1 to avoid failure. Then here we have a concept of allowable stress value. Okay, so for design purpose, we'd like to provide the allowable, the safety factor in advance. Okay, if you open design code, they set a certain value of the safety factor. Let me check. For example, let's say safety factor is 1.2, for example, and then my yield strength value Fy is 100 megapascal. Then the stress that I can use is what? Allowable value is Fy divided by the safety factor. Then this is equal to what? 100 divided by 1.2. This is equal to, if I use my calculator, it's around 83 megapascal. Okay, so in actual stress strain diagram of the material, and let's say this is the yield strength value, and then this is the allowable stress value, sigma allowable, and that was equal to 100 megapascal in our calculation. The allowable stress value is 83 megapascal with n is equal to 1.2. Okay, so any stress calculated by the external force divided by cross-section area. This is the normal stress caused by the external force. For design purpose, so I'd like to control, the normal stress by the external force is less than or equal to this allowable strength value for design purpose. Is it clear? This is how we design, okay? And then you may be interested in the brittle material. I discussed only the steel ductile material, where we use the yield strength value for the reference strength. For brittle materials, we use ultimate strength value instead of yield stress. Okay. For strengths, for most of design code, they use F to represent the yield strength value, the Fy, the ultimate strength value, Fu, and for shear strength, F tau. Okay. Then once we have allowable strength value, multiplying allowing stress and the cross-section area, then we can determine the force, allowable force, and the shear and the bearing also. So let's consider this design example. So here we have to determine the allowable force here. This is the example here. Okay. So how many failure criterion that we have? So first, the failure criterion that we have to consider is tensile failure, isn't it? Tensile failure. And also, we need to consider shear failure. And then third, we have to consider bearing failure. Okay? For these discussions, for design purpose, first we have to determine the safety factor. Safety factor for this example, let's consider, I want to consider safety factor is 1.4, for example. Okay. The specific value of the safety factor depends on design code and the problem that we have to consider in design. Okay. Okay, first let's check the tensile failure. So tensile failure, we have to check here and also here. Okay, and then let's determine the allowable normal stress. The allowable normal strength is equal to, by the way, because we use the concept of F, I want to use F, not to confuse. So F sigma allowable is equal to, so if I want to use, the yield strength value, Fy divided by the safety factor, isn't it? Okay, then we have this allowable normal stress value. Okay, so for the tensile failure, my allowable force P is equal to what? So minimum of the tensile force case 1. The case 1 is using this area, and then case 2 is using this cross-section area, isn't it? And then for the shear failure, so we already discussed how we calculate the shear failure when we design the bearing, when we discuss the bearing stress value. So you need to consider the shear area here, for example, here, for the blue part, and for the gray part, we have to consider the shear area here. Okay? And then the next step is we need to consider the bearing stress. The bearing area, where's the bearing area? This is the bearing area. Okay, that's it. We discussed all the subject in the lecture note 1. By the way, here for design purpose, if you want to determine the dimension, the required area can be easily determined. First, we have to determine the internal force to be transmitted by the external forces and then the geometry, and then dividing the internal force by the allowable strength value, then we can determine the required area very easily. For the detailed calculation, please play with my TA. Alright, so let me start my lecture here. So if you have any questions, please send me an email to my email address. Okay, so if you don't have further questions, I'd like to finish my lecture here.